today I will talk about the different applications of metasurfaces. But let's start from the history. So the basics of optical theory have been laid more than 2 centuries ago, and almost immediately the first camera prototypes have emerged. And in the beginning of 20th century, it was possible to buy the photo camera. It was extremely expensive, but it was possible. And up to the last years, nothing changed in the construction of the photo camera. In contrast, the image processing and recording constantly changes. Each 30-40 years, we have the evolution from the writing on the silver plates, plumb plates, colloidal solutions, and Polaroid, CCD, and CMOS matrices. And the question is, this is good or bad that here we have the constant changes and here nothing has changed? I think it was quite okay up to the last years, because today we come to the limitation. Please look at your phones from the side view like this, yeah, and tell me what is the most thick part of this of your phone. This is camera. Camera is the most thick part, and the optics doesn't allow to make your smartphones even thinner. Why? Because the classical optics operates, so to obtain good image, we need a lot of lenses, mirrors, filters, polarizers, etc. All these classical optical devices are relatively thick. The thickness may reach thousands of wavelengths, so up to the millimeter, and usually they perform only one function and are limited by some classical approaches. And it highlights the relevance of resonant photonics, which operates with deeply subwavelength objects that may be multifunctional, so perform several functions simultaneously and even overcome, for instance, diffraction limit. The platform of resonant photonics consists of metasurfaces, metalenses, different nanostructures, and nanoparticles, and I will focus on metasurfaces mainly in this talk. Metasurfaces are two-dimensional periodic subwavelength arrays, and they are very thick, very thin. So the thickness is from several atoms up to several nanometers in visible spectrum and up to the 1 millimeter in microwave spectrum. Okay, and we can divide all the applications related to metasurface into 2 branches. In the far field, we consider the metasurface as the reflectors, refractors, absorbers, polarizers, lenses for plane waves. In this case, we are working inside the light cone at this dispersion diagram, so the dependence of energy on momentum or frequency on the wave vector. However, for some applications, we need to manipulate the highly localized light, to manipulate the light propagating almost in 2-dimensional space. And in this case, we go under the light line in the so-called near field or dark field region. The typical carriers of near field localized light are surface waves, surface plasmon polaritons, and guided waves. Okay, that was my introduction about what is metasurfaces. And within this talk, I would like to tell you about 5 applications with absolutely different metasurfaces, metal metasurfaces, which are called plasmonic, with completely dielectric metasurfaces. And I hope that I will prove you that this is a perfect tool for many tasks in absolutely different areas. So I would start from the Brewster's angle microscope. So it is well known that at the interface between 2 media, we can achieve the Brewster angle when the reflection of TM polarization goes to 0, completely to 0. Right? At the interface between air and glass, this angle is close to 55.4 degrees. Now we will add the 2-dimensional layer, which we consider as a specific electromagnetic boundary interface. And the Fresnel coefficients will change, and we can observe the shift of the Brewster angles. In this case, we add the two-dimensional layer of the 1 millisiemens conductivity, and it shifts the Brewster angle by about 8 degrees. It's interesting that if we add the imaginary part for conductivity, which should be presented according to Cramer's chronic relation, the angular position of Brewster angle doesn't change, but the amplitude of the dip will decrease. Yeah. Okay. So next we study the shift of Brewster angle for different materials. We start from the monolayer graphene interrogates region, and you can see here the color map showing the value of reflectance depending on angle of incidence and frequency. Green line shows the conventional Brewster's angle without this two-dimensional layer, and magenta line shows the Brewster angle for the case of monolayer graphene put between air and glass. So we can see that it shifts more and more for lower frequencies. Another more difficult structure is optical metasurface obeying to the Lorentz model. So it has the resonant, and therefore here the dependence of modified Brewster's angle is non-monotonic. It has some peak, yeah, and if we will show on the shift of this delta, so the difference between modified and standard Brewster's angle, it also has peaks that reach almost 20 degrees. Okay, and of course we would like to, so here we use some effective model, and now we propose the real design of such a metasurface consisting of periodic array of gold nanodiscs of 20 nanometer thickness. So here you can see the reflectance, transmittance, and absorbance for 3 different cases. The interface between air and glass without two-dimensional layer, with ideal two-dimensional layer of surface conductivity 3.5 millisiemens, and for the this metasurface. So you can see that initially in the right part we have the fields at 2 angles. The top part shows the reflected field, the bottom part shows the transmitted field. So initially we have the Brewster angle 55 degrees, right? And for this case, when we add two-dimensional layer, the Brewster angle shifts to 72 degrees. And we can see that this case and this case are pretty identical, except the region very close to the interface. So this metasurface works pretty close to ideal two-dimensional layer with this conductivity. Okay, it was first application. The second one, it is related to the transference signal in plane. Yeah, so it is important for different planar technologies. If we will throw the stone into the water, we will see such a water waves propagating along the surface between water and air. And we can excite the same surface waves, but electromagnetic ones. It is more difficult to excite them than just throwing the stone, but this is possible to do, and they're called surface plasmon polarities. And the problem for the transferring energy is that they propagate radially in all directions. And if I need to transfer the signal from this source to this receiver, I will the almost whole energy will be lost. So the efficiency is extremely low in this case. And what I want to do is to realize the so-called canalization region, which means highly directional, diffractionless propagation of surface waves. So the waves is still highly localized, but it propagates along one direction. So in this case, the efficiency of signal transferring is pretty high and may reach almost 100%. Okay, and to do it, we will use the hyperbolic metasurfaces. So what does it mean? So first of all, we will consider periodic pattern of such a gold nanodiscs or gold nanopatches. And you can see that they are isotropic inside the unit cell, but they're resonant. So if we will look on the dependence of imaginary part of conductivity, it will have some resonance, and we can distinguish two regime when it is negative and positive. Now, if we will introduce the anisotropy degree, for instance, we will stretch the particles, the resonances will split into two resonances, and the third regime emerges when the imaginary part of conductivities have different signs, and this regime is called hyperbolic ones. Why hyperbolic? Because if we will now look in the isofrequency contours, so the contours at the same frequency in the wave vector space, in the reciprocal lattice vector spaces, for this isotropic case, it will be the left column, so it will be always the circles. The yellow circle shows the light line in vacuum. But for the anisotropic, it will be first ellipse, then it will transform to such a hyperbolus, then to these flat lines, and again to the vertical ellipse. This transition is called topological transition, in photonic topological transition. But this regime, when we have two flat lines, corresponds to the canalization regime when wave propagates along the specific direction. So now we engineer the metasurfaces in such a manner to optimize this canalization regime. So here you can see the distribution of magnetic field excited by vertical point dipole, and the energy propagates along specific direction as we want. We can do it even with this double layer, bilayer metasurface, and here we use more difficult combination, but in microwaves we use such a unit cell and then rotate one layer with respect to another one at the canalization regime. And in this sense, we steer the canalization, we change the direction of propagation in the canalization regime. This is the experimental simulation and experimental results in microwaves. Okay. The obvious advantage of all-dielectric metasurface is that they have negligible absorption losses, and this is also important for us. And first of all, I would like to consider the following fundamental problem. So it is well known that the eigenmode spectrum of isotropic bulk medium is double degenerate with respect to polarization. In other words, the group velocities of TE and TM, fundamentally polarized plane waves, are absolutely the same at any frequency in any direction. And due to this fact, we can easily manipulate the polarization of light. So to change the polarization, we just need to break this degeneracy by introducing some anisotropic material, usually uniaxial crystals. This is the simplest way, but there are a lot of ways. But if you will break this degeneracy, you can change the polarization on demand. From the other hand, in the modern epoch of miniaturization and planarization, we would like to work with highly localized light, under the light line. The simplest example is the electric slab waveguide. But in this case, the polarization degeneracy is lost because the dispersions of TE and TM guided modes do not coincide generally. So we bring the high localization by loss by the polarization degree of freedom. And we propose a new platform, such as nanostructured metasurface, which will support the guided waves that are highly localized, but at the same time they are degenerate. So this platform discovers both high localization and polarization degree of freedom. In the simplest approximation, we can represent it as the structure of dielectric slab waveguide. But to be more specific, we play with so-called resonances in nanoparticles, and the process is a bit more difficult, but I skip the details and show just the results. So we will consider the square array of such a nanocylinders, and you can see that eigenmodes are orthogonally polarized, and the dispersions of T and T modes are pretty close to each other. Indeed, they are not degenerate completely like in quantum mechanics, right? We just engineer them to be very close to each other. And in principle, it may be realized for different frequency range, for different materials. And here we show the design, for instance, the ratio of cylinder that you need to achieve the polarization for different localizations degrees. And to do it, we need two main criteria must be fulfilled. First, we should have the weak dispersion of material and low absorption losses. If it works, you can use these approximate designs to find the polarization degenerate designs in gigahertz with ceramics, silicon in infrared, and many other materials in near infrared. And to prove these results, to verify them, we do the following experiment. We make the chain of ceramic cylinders in microwaves. We excite the waves here and use by some loop acting as a vertical magnetic dipole, and use the same loop for scanning the field. And then we apply two-dimensional Fourier transform to retrieve the isofrequency contours and dispersions. And you can see here the simulation and experimental results for T and TM polarization they taken together. And one can see that they are pretty close to each other, and the delta K, so the difference between T and TM modes at the same frequency are shown here. And the degree here is 10 to minus 3 in P over A unit. So practically it means that such a guided wave can propagate along 100 of unit cells, 100 of periods before achieving some sensible fast delay. So it works. And based on this discovery, we do the obvious application. It's planar polarizer of guided light, working exactly as the classical quarter wave plate. So how quarter wave plate work? We excite the plane wave with a linear diagonal polarization. It comes to some uniaxial crystals, and the length of this uniaxial crystal is that at the output it gives pi over 2 fast delay, so the polarization becomes right circular. We do pretty the same story, but instead of vacuum, we use the metasurface with polarization degenerate spectrum, and instead of uniaxial crystal, some other modified metasurface where the degeneracy of T in TM modes is broken. So the idea is pretty the same as quarter wave plate, but we do it for guided waves, for highly localized guided waves. Therefore, we call it guided wave polarizer. And that's what we measure. So we measure the field in this cross section before this guided wave polarizer and after it. And we can see that polarization before was linear, and then it becomes circular. So this black shapes show the polarization in the specific points. Colors correspond to the polarization Stokes parameters. In the left is the theory, the right is the experiment. In the experiment, we didn't excite exactly linear polarization, but rather diagonal elliptical polarization. But still, one can see that it is rotated by 90 degrees, so still this polarizer works exactly as quarter wave plate, but for the guided waves. The next application is devoted to the anti-reflection coatings for solar cells, especially for the silicon solar cells. Why for the silicon? Because while we fight for each percent of efficiency for solar cell, indeed we lost about a half of energy due to the reflection at the interface between air and silicon. And this is, of course, the problem. And the typical way to fight it is to use anti-reflection coating that suppress the reflection. It may be done by a thin dielectric layer, and it can perfectly suppress the reflection, but only for the single frequency, for the single wavelength. So it means that in the broadband region, it doesn't work. Even if you use 2 or 3 layers, which is much more difficult, both from fabrication point of view and from the just it increases the cost, the price of this coating. In this case, the wavelength region where we suppress the reflection is usually doesn't exceed 300 nanometers. But the solar radiation is high in whole visible and near infrared range. So we should suppress the reflection in whole this range. And to do it, first of all, we propose the single layer, what is important, just single layer anti-reflection coating based on silicon metasurface. So one can just modify the silicon layer for this. And it consists of such a periodic array of cross-circle particles. So the particle consists of like cross and circle with these parameters. We start from this, and then we drew some more advanced artificial intelligence optimization. So we substitute each pixel by the presence of silicon or its absence, and the algorithm pushes many calculations to find the best designs, and in our case it comes to this one. Here you can see the distributions of reflection dependence of the angle of incidence and wavelength, and one can see that it works pretty well except this triangle for both cases. I don't remember the exact numbers, but the total the reflection under the integral average reflection at normal incidence is about 1%, I think, 1-2%, and total integral average reflection over angles and wavelengths is about less than 5%, let me say. And finally, we compare the just bar silicon air interface with standard one layer dielectric working at the single wavelengths, and red and green line corresponds to two designs proposed here using forward and inverse design techniques. So they work much better. And the last part is devoted to the light collection to optical fibers. Optical fibers are absolutely brilliant tool for many applications, for telecommunications, for remote applications where you need to collect the light remotely to detect something remotely. These are widely used in medicine, endoscopy, laparoscopy. These are widely used in space technologies, etc. But there is one problem. We called it in-coupling efficiency. So this is the efficiency of plane waves incident on the fiber. I mean, under coupling efficiency, I mean the efficiency of the transformation of these plane waves into the guided modes of the fiber propagating for long distances with negligible losses. And it is pretty ideal at normal incidence, but it rapidly decreases under oblique incidence, such that for angles like 15 degrees, it's too small for practical applications. And this is, of course, a big limitation. And we propose to resolve it by using lab fiber concept, which means again nanostructuring the fiber, and we will nanostructure the tip of the fiber. So we propose the following concept. This has an axial symmetric all-dielectric nanostructure. So again, it first of all, it doesn't have the absorption losses. Secondly, axial symmetry brings the independence on the azimuthal angle, so only the angle of incidence matters, and it's pretty independent on the polarization. And this nanostructure acts as a diffraction gradient, but the first diffraction order coincides with the fiber axis. So we just load all the energy in the first diffraction order, and each coincides with fiber axis, so the coupling is very good. Again, I skip the details of analytical and numerical models, but my colleagues in Leibniz Institute of Photonic Technologies fabricated the following axial symmetric, like concentric rings nanostructures using quite difficult technique, including electron beam lithography, ion beam etching, and following resist removal. And you can see here 7 single mode fibers, commercial single mode fibers. The central one is unstructured for reference, and all others are structured by different number of rings. And this is a central result. You can see the gray dashed line corresponds to the bar fiber without nanostructure. Polar lines correspond to the nanostructured fibers with different number of rings. It's an experiment. This is simulation. And one can easily see the great enhancement at the large angles more than 60 degrees, like we engineered it, like we designed it, with the maximum around 75 degrees. This insert shows the output, output image recorded by infrared camera at normal incidence and oblique incidence for nanostructured fibers. So it is the same. Then we use more advanced technique, which is called direct laser writing or 3D nanoprinting, to produce the nanostructures very quickly, quite precise, and also controlling the width of each ring, height of each ring, the distance between any two rings. They are done from polymer with refractive index about 1.55. And it opens new degree of freedom for us. And first of all, we do such a double pitch grating, opening second diffraction channel, and we have 2 peaks here. Here the dashed line corresponds to the simulation and solid lines to the measurements. And we also do the aperiodic nanostructure where each ring has been separately optimized, and it works like quasi-flat wavefront, so the coupling efficiency is pretty high, but almost doesn't depend on the angle of incidence. And we can compare all these results. So the color range here shows the range of angles where we achieve the necessary level of coupling efficiency. For the just periodic axial symmetric gratings, we have the good efficiency at the small angles and in the vicinity of the resonance. But for the nanostructures shown in this slide, we cover almost whole angular range. And for the fiber without nanostructure, the covered range is typically up to the 12-11 degrees. And the last part, which I think is the main and the most powerful result, we use the multicore fiber now, and we consisting of 7 cores that are independent from each other. So the guided wave propagating along each core do not interact with each other. And we add 7 different nanostructures at each core. That's how it looks. That's how it looks. Yeah, it's the same images. And each core is optimized to couple the light at the specific angle of incidence, like 20, 30, 40, 50, 60 degrees, etc. Here you can see the measurement result. This is a measurement result, and this so we have 7 lines corresponding to the measurements from 7 cores. And here, this is the integral signal from whole fiber. solid line corresponds to the simulation and dots to the measurements. So we increased even more the light collection. Comparison with black and gray line corresponds to the bar fiber without structure. So the improvement is very high, because also pay attention, please, that this is logarithmic scale here. Again, we will draw this diagrams with color range. One can see that the efficiency more than 1.1% covering for all angular range, and more than half angular range are covered the coupling efficiency more than 1%. So before that it was 10 to minus 4, 10 to minus 6%. So we increased the coupling efficiency in several orders of magnitude. Okay, and this video shows what we see from the camera at the output from the fiber. So when the input we have these 7 cores with 7 nanostructures, and the output we see the following figures depending on the angle of incident changing here. So you can see that at different angles of incident, different cores are illuminated, and depending on the combination of the illuminated cores, we can understand what is the angle of incidence. So this fiber is also can work as so-called angular demultiplexer if we will consider inverse task. So not collect light but illuminate light from the fiber. But also we can analyze the angular distribution of radiation of some indefinite source. We can do it remotely with this structured multicore fiber. Okay, and finally we did it, of course, for multimode fiber using the same principles. And one can see here this graph, for instance, shows the enhancement of nanostructured fiber related to the bar fiber. So before the numerical aperture limit, we don't have the enhancement, but after that it rapidly increases, and for the angles more than 43 degrees, the enhancement is always more than 1000. So this is 1000 times of enhancement. So to conclude, I have shown you that like correctly optimizing and engineering the metasurfaces, we can achieve many goals for absolutely different applications, such as Brewster angle microscopy, in plane plasmon canalization, the polarizers of the localized light, anti-reflective coatings for solar cells, and light collectors, fiber-based light collectors. I would like to thank the Alexander von Humboldt Foundation for supporting me during these works, and I would like to announce that me and my colleagues plan to launch the Ukrainian Optical and Photonic Society, aiming to connect together the international support to boost the researchers and educators in Ukraine. And I would like to thank the Armed Forces of Ukraine for this service. It's absolutely incredible that we can do some science under these difficult circumstances. Thank you for your attention.